Okay, let's start by looking at this problem right here. We're supposed to find out what the limit of this sequence is as n approaches infinity. To give us an idea of what we think the answer is, let's go to Desmos. Problem number 14. I've set up this table here, and this little button right here says bring all the elements of that table into focus. So there they are. Normally when we talk about a sequence, we're not graphing a function, we're graphing a series of points, because the domain is a set of positive integers. So normally if we're just displaying a sequence, we don't show the function. Okay, so it looks like, well, if I do graph this and pan out, it looks like we're approaching negative infinity here. And the table seems to confirm that. As n gets bigger and bigger, the y values get smaller and smaller, bigger in absolute value, but more negative. And by the way, so let me click this button right here to bring into view again all the elements of the table. It looks like f sub 10 of 100,000 is negative 600,000. So that seems to confirm what we're looking at here. I can hide these two, by the way. Question is there a way to deduce that the limit is negative infinity without actually graphing the thing? So let's see if I can go here and talk about, well, let me give you, how you would know to do this is based on experience and seeing other examples. But if I divide every term of this function, top and bottom, by n to the fifth, the biggest expression, the biggest value in the denominator, I would get negative 6n plus sine squared of 9n didn't write that very well, over n to the fifth, all over 1, because I'm dividing by n to the fifth, plus 17 over n to the fifth. Okay, and by previously proved limit theorems, this is the same as the limit of, as n approaches infinity, of negative 6n plus the limit as n approaches infinity of sine squared of 9n over n to the fifth, all over the limit as n approaches infinity of 1 plus the limit of 17 over n to the fifth as n approaches infinity. And what we want to do is focus on these terms right here, this one and this one. Of course, the limit of a constant, this guy right here, is just 1 plus, and as n approaches infinity, this expression approaches 0 because I get numbers like 17 over 1,000 to the fifth power, very small, so its limit is 0, and there's a theorem that says that. We still have the limit as n approaches infinity of, well, I can put the negative 6 out front if I want. And what's the limit of this thing? Well, I can find that limit using the sandwich theorem. So the sine squared of 9n has to be between, well, actually, let me take off the sine squared. Sine of 9n has to be between 1 and -1. And now if I divide every term by n to the 5th, and n is positive, I get this. And if I square all three parts, oh no, I have to have sine squared here. Well, the idea is that this limit right here, this is like a sub n, b sub n, c sub n. This limit is 0, this limit is 0, so this limit has to be 0. And if its limit is 0, then if I square the numerator, the limit will still be 0. So this is a plus 0 also. Again, this limit is 0 by the sandwich theorem. And so this is going to be -6 times infinity, which equals infinity. Again, infinity is not a number, it's a behavior. I should say negative infinity, because -6 times a very large positive number is a negative number in absolute value. So the answer to this problem is negative infinity. Okay, so I'm going to end this video, and we'll go to the two problems involving factorials shortly.